Hello students, good morning all of you. This is your Prabhakar and welcome to our channel Dawn of Chemistry. Right. Hope you are happy and healthy in your homes. Stay home, stay safe in this pandemic situation. And in this today video, I am going to explain about the hybridization part 2. So why I made this part 2 means, you know very well, this is a very vast topic. So I have divided total theory part in one part and competitive part in a different part. In this part, we are going to explain about the how they will ask questions based on the hybridization, and up to advanced level how they can go to the extent of asking questions. And this is our first video in how many ways they can ask questions on a particular concept. So far I have done so many videos. In any concept we didn't discuss about the types of problems, what they can go, or extent of how they will asking questions, to how much extent they can go when they are asking questions. In this video only we are going to cover all the types of models, how they will be asking you based on this hybridization topic. And in the further videos also I will make different videos on how they will ask questions on that particular topic also we will do. Right, let's get into the details. Hybridization part 2. Right, see, in this part we are going to discuss about what kind of d orbitals involved in the hybridization. What kind of d orbitals involved in the hybridization? Kind of d orbitals involved. We know very well that d orbitals we are having dx square y square, dz square, dxy, dyz and dxz are there. So in which hybridization, which orbitals involved, why they will be involving like that, and what is the geometry resulting because of the mixing. Let us see. When you take dsp2 hybridization, this is a square planar complex. dsp2, because of dsp2 hybridization we will be having a square planar complex. If you take for example, there is a molecule AB4. A will be in the center of a square and all B atoms will be surrounding. How they arrange means, the orbitals of A, one d orbital, s orbital and two p orbitals will combine with one another and they will arrange the four orbitals into the four corners of a square, resulting into this. So since they are present into the four corners of a square, you know very well which orbital will involve or which orbitals lie along the four axis dx square y square. Since dx square y square lies in the four, you know very well dx square y square. The shape of dx square y square is, this is 1 and this is 1. Along the x-axis and along the y-axis the orbital will lie. So that's why in dsp2 hybridization dx square y square orbital will be involved. Since the lobes are present into the corners of a square, and here also lobes are present into the corners of a square, and only one orbital is there, they are present in this dsp2 hybridization. If you can take sp3 dehybridization or dsp3 hybridization, the structure resulting into trigonal bipyramidal. So the structure of the molecule is trigonal bipyramidal. This one is AB4 molecule. If you take AB5 molecule, A will be in the center, B will be into the corners, and B and B will be above the plane and below the plane. So since there are axial orbitals are there, because of sp3 hybridization tetrahedral will come. Since D is involving, it will go into the axial position. There is only one orbital which will be present in the axial position, that is dz square orbital. Since dz square orbital lies along the axial position, this also will be involving in this sp3d hybridization. So since into the four corners of a square they are present, dx square y square will involve. Since here two axial bonds are there, dz square will involve. I am writing in a distant manner. Now one more concept is there that we will also discuss. Let us go to the another hybridization, sp3d2 or d2 sp3. So in this hybridization, which orbital is involved in the hybridization? So see here, sp3d2 or d3sp3, the shape of the molecule is square bipyramidal. This is also known as octahedral. The molecule example is AB6. A will be present in the center, B atoms are present into the corners, and 1B will be above the plane and 1B will be below the plane. Since here you see, because of square planar, dx square y square is there. Because of axial position, we are having the dz square is there. Because of this thing here, dx square y square is involved as well as dz square also involved. Since in this case all four are present into the corners and this is onto the axial position, both the orbitals will present in this hybridization. And next you see Pentagonal Bipyramidal, that is sp3d3. In this sp3d3, the shape of the molecule is Pentagonal Bipyramidal. The structure of the molecule for Pentagonal Bipyramidal is, see, a pentagon. Example for this thing is AB7, that is IF7 you can take. A will be in the center, B atoms will form a pentagon, and one atom B will be axial position, another atom B will be in the equatorial position. So in this case you see here dxy, dyz and dxz orbitals are involved here. Since though they are present into the plane as well as axial position, these three orbitals combinedly together forms the sp3d3 hybridization. This is the exceptional case. Though they are axial bonds, these three together will combine. When they are combined means axially you can have a distorted position and you will be getting this thing. Pentagonal bipyramidal structure is there means you can get this answer. So like this we can understand. Like this they will ask you, or we can easily explain the structure of DSP2 hybridization, sp3d hybridization, sp3d2 hybridization and then sp3d3 hybridization. This is one kind of asking questions, which orbital involved and how to understand that thing. Next, one more important thing is there, that is what are the bond angles between them. So if you say for example BAB, we call the bond angle as BAB. Normally we study, what is the bond angle we study? What is the bond angle in tetrahedral structure? What is the bond angle in linear structure? What is the bond angle in trigonal planar structure? But how many bond angles are there? That is a different kind of asking questions. Listen carefully. How many bond angles of 90 degrees are present in square planar? How many bond angles of 180 degrees are present in square planar structure? Like that they will ask you. Listen carefully. So here you see BAB, you know very well. When you take a square, here this is 190 degrees, this is 190 degrees, this is 90 degrees and this is 90 degrees. So totally 4 are there which are equals to 90 degrees. So how many angle BABs are 90 degrees means 4 will come. This is a very very important model of asking questions. How many BAB angles are equals to 90 degree? How many atoms are perpendicular to one another? How many atoms are anti to one another? Perpendicular to one another means 90 degrees will come. Anti to one another means 180 degrees will be coming. Here you see 180 are how many? This is 180 and this is 180 will be coming. Here you see these are anti to one another. This both are same actually. This is 180 and this is 180 will be coming. Are you understanding? Right. So like this we can easily understand how many 180s means 2 180s are present. Let's get into the trigonal bipyramidal. In this trigonal bipyramidal, angle between BAB is 120 degrees. How many are there? And there are 90 degrees bond angles are there. How many are present? Let me tell you this using example. In the previous class we discussed about trigonal bipyramidal means one atom will be in the center, one atom, three atoms will be onto the three corners of the triangle. One atom will be above the plane, one atom will be below the plane. So here you see the atom above the plane is making an angle of 90 degrees with the atom present in the plane, right? So that's why the above the plane is making bond angle with this thing. So one angle BAB is 90. Like this with three atoms from the above position 390 degrees are there, and bottom also you see with respect to the bottom atom also it is making three angles, and hence the 90 degree angles in this case will be above 3 and below 3. So total 6 are there. How many 120s are there means in the plane 3 atoms are there, so 120 degrees. How many BABs are 180 degrees? How many are there means only one will be there, that is one angle is 180 degrees will be coming. So like this we can easily understand how many angles 180. Here you see how many angle BAB is equals to 180 degrees means 1 will be there. This is for trigonal bipyramidal. For example, if there is a square bipyramidal, so in square bipyramidal you see this is a square. So from the axial position 490 degrees, from bottom 4 are there. Trigonal pentapyramidal means from top, here you see pentagonal bipyramidal also from the top 90 degrees will come and from bottom also 90 will come. Let us see how many 90 degrees will come in this case. One is axial, one is this one. So angle BAB is equals to 90 degrees, angle BAB is equals to 180 degrees. So see here 1, 2, 3, 4. From axial, in the plane 4 are there, above the plane 4 are there, below the plane 4 are there. So totally 12 BABs are equals to 90 degrees. And how many are is equals to 180 degrees? This is important thing. Here you see this is 180 degrees, this is a 180 degrees and this is a 180. So totally 3 180 degrees are present in case of the octahedral structure. In octahedral structure, how many angles are equals to 90 degrees? How many angles are is equals to 180 degrees? Like that they will be asking you the question for this. And next you see SP3 D3 hybridization. In this, angle BAB is equals to 90 degrees are there, angle BAB is equals to 72 degrees are there, angle BAB is equals to 180 degrees are present, and angle BAB is equals to 144 degrees are present. Like this they will be asking you. Even you see in this case also you can ask you how many angles are 240 degree angles are present. Like that also they can ask now. Right. Angle BAB 90 is what? Axial, above the plane 5 will be coming and below the plane 5 will be coming. So totally 10. 72 in the plane, 5 will come. 180 only this will show. So 2 will come. 44 will be how many? This is 1. This is 1. This is 3 and this is 4 are there. You can have 4 will be coming. Like this, by using this hybridization structure of the molecule, we can easily understand how many types of bonds are present and how many bond angles are 90 degrees and how many bond angles are 180 degrees. So be careful with this thing. Take down this for 1 minute. This is very important one, ma'am. Which orbitals involved in hybridization? What will be the bond angles between them? This is very important chapter, ma. From this only, definitely whatever the question they ask you based on the structure, from this concept only there is a chance of asking possibility. You take any compound in the inorganic chemistry, they have to come to the structure, means hybridization concept. Definitely they will touch one question. So be careful with this thing. Right. Hope you have taken down this thing. Right. Let us see how to find hybridization in case of complex compounds. Complex compounds. So see, in complex compounds we say them as inner orbital complexes, outer orbital complexes, inner orbital complexes means n-1 d orbitals will be involved in the hybridization. Compared to ns and np, compared to s and p, n-1 d orbitals will be involved in this case. Outer orbitals complexes means nd orbitals will involve in the complex formation. Inner orbital complexes are known as the low spin complexes. Outer orbital complexes are known as the high spin complexes. High spin complexes. Mostly outer orbital complexes will be favored when the ligand is outer orbital inner orbital complexes will be obtained when the ligands we are having is ammonia, carbon monoxide, ethylene diamine. These are known as the strong field ligands. Whenever the ligands are ammonia, carbon monoxide and then ethylene diamine and pyridine, whenever these are present as ligands, then we will be getting the inner orbital complexes, and it is not mandatory. See carefully. When they are present, there will be no doubt they will be forming the inner orbital complexes, but not mandatory. Subject to the availability So see, here always strong field ligand will not guarantee your inner orbital complexes. It is subject to the availability of n-1 d orbitals. Let me explain how this subject will availability of n-d orbitals will explain this thing. I am taking examples of NiCl4 -2, NiNH3 +2, NiNH3 6 and PtCl4 -2. and then FeCN6 minus. To understand this thing, you should be very careful about the electronic configurations of the element. So let us see how we will be coming. Nickel electronic configuration is argon 3d8, 4s0 and 4p0. For this thing you have to write the orbital completely. 1, 2, 3, 4, 5, 6, 7, 8 according to the Hund's rule and then Pauli's exclusion principle. You have to write down this thing. And for nickel also is present in +2 oxidation state. Here also nickel is present in +2. So it will be coming argon 3d8, 4s0, 4p0 will be coming. So 3d8 means you know very well. 1, 2, 3, 4, 5, 6, 7, 8 will come. 4s is present and then 4p is present. So let us see, in this case, whatever there is the possibility, always remember strong field ligand is coming means because of the electron pair on it, it will force the incoming electrons to get repelled. So since this electron density is repelling the existing electrons, the electrons will pair up. 1, 2, 3, 4, 5, 6, 7, 8. The electrons will pair up according to the Hund's rule of maximum multiplicity. Because of the strong field ligand, the electrons will pair up against the Hund's rule of maximum multiplicity. So that's why they will pair up here, and 3d orbital is available, s orbital is available, and 2p orbitals, and hence it undergo dsp2 hybridization. So that's why NiNH3 is dsp2 hybridization, and it is a square planar complex. So listen to this very carefully. Whenever strong field ligands are there, they will force the electrons to pair up within the orbital against the Hund's rule of maximum multiplicity. In NiCl4, you see, by looking at the 4, you need 4 hybrid orbitals. So that's why 1s orbital and 3p orbitals are there. So it will be sp3d hybridization. So it is a tetrahedral molecule, and this is a square planar molecule. And NiNH36, you see, here you see inner orbital complex. Since there is a strong field ligand, this is a inner orbital complex. Let us see NiNH36. Nickel is present in +2, so argon 3d8, 4s0, 4p0, 4d0. So 3d8 means 1, 2, 3, 4, 5, 6, 7, 8. 4s0, 4p, and here 4d will come. Here I am not going to this platinum complex. So see, because of ammonia, they get paired up. 1, 2, 3, 4, 5, 6, 7, 8. 1 is available, but you need sp3, 6 hybrid orbitals you need, but here only you are having only 1 is available. You need 6 orbitals. You can say 1d from here, 1d from here. That is not possible. No? There is no dsp3d hybridization. So if there is availability of 2 inner orbitals, it will be d2sp3 hybridization. But here only 1 orbital is available, and hence it does not take the inner orbitals. It will take the outer orbitals and forms sp3d2 hybridization. Though it is having strong field ligand, it will be forming the outer orbital complex. So since it is forming outer orbital complex, number of unpaired electrons is 2 will be coming, and it is a paramagnetic compound. So be careful with this thing. So why it is an outer orbital complex or sp3d2 hybridization means inner orbital is not available, so that's why it will take electrons from the outer orbital and it will form. If you see PtCl4 -2 is an exception. In this platinum case, the configuration is krypton 4d8, 5s0, 5p0. Though chlorine is a weak field ligand, it behaves as a strong field ligand because of platinum, and it behaves. So this is an exceptional case. Though there is weak field ligand is there, it is a low spin complex. Why? Because chlorine behaves as a strong field ligand. Let us go with FeH2O6 and FeCl6. Hope you are understanding. So in nickel Cl4 minus, there is availability, there is not possible of availability of inner orbital complex, so it will be forming the sp3 hybridization. In this case, there is availability of inner orbital, so it will be forming the dsp2. Here only one is available, other is not available, so it will be forming. Let's see here, argon 3d6, 4s0, 4p0. So it will be forming like 1, 2, 3, 4, 5, 6. Here argon 3d6, 4s0, 4p0. 1, 2, 3, 4, 5, 6. Since it is a strong field ligand, 4s is empty and 4p is empty. 4s is here, 4p is here, and then 4d also here. Since it is weak field ligand, it will not pair up, so it will take electrons from outside and it will be forming sp2d. Because of presence of strong field ligand, it will force the electrons to come and pair up. So they will pair up here and 3d orbitals is involved, so that's why it will be forming the d2sp3. So here it will be forming d2sp3, here it will be forming the sp3d2. Here you can work out on this inner orbital and then outer orbital complexes. In this inner orbital complexes and then outer orbital complexes, you can find like this. N is equals to number of unpaired electrons, 4 are there. Magnetic moment is equals to root over n into n plus 2. By using these formulas, you can identify the magnetic moment of the species also. Finding this also very important one. Since the situation has come, I am explaining here only. We will discuss that about in a different video, but try to have a note of this thing. By finding the hybridization of the particular complex, you can identify whether it is paramagnetic or diamagnetic. You can identify the Bohr magnetic moment and you can identify the color also. If unpaired electrons are present, means it will be colored in nature. There is no unpaired electron, means it will be having no color. Let us see, for example, NiCO4. Nickel is in zero oxidation state, so it will be argon 4s2 3d8. Because of strong field, it will pair up completely in d orbital. So no d orbital is available, so it is sp3 and it is a tetrahedral structure will come. So be careful with the nickel tetracarbonyl. So whatever there is, inner orbital complex or outer orbital complex, that is completely dependent on whether the inner orbitals are available or not. Mostly strong field ligands like ammonia, carbon monoxide, ethylene diamide, pyridine, and then cyanide is there. Definitely they will favor the inner orbital complexes, but not always. That is very, very standard thing. So keep that in mind. Right. Take down this thing. Next we will see how to identify hybridization for some abnormal molecules. Based on the number of bonds you will be having, but now there is no need of number of bonds. Simply how to identify. Take down these things. So be careful with this concept. So always strong field ligand does not guarantee you the inner orbital complex. That is very, very important thing. Right. Hope you have taken this thing. Let us see. For some important compounds are there, and these are the common compounds we will be encountering in the exams. How to identify hybridization in these complexes, let us see. How to identify the hybridization in some common compounds. Let us see XeF6, XeF4, XeF2, XeO4, XeOF4, ICl3, H2O, NH3, IBr5, IF7, mostly xenon compounds will be taking, ammonia and this one. So let us see for this kind of compounds, I3 minus, already we have discussed it for that thing. So let us see in these kind of compounds how to identify the hybridization. Same formula we will be using. Hybridization is equals to half into V plus M minus C plus A will be coming. Here I want to tell you about the bond pairs and the lone pairs also. Number of lone pairs is equals to number of hybrid orbitals minus atoms surrounding central atom. Here I am telling you how to find the lone pairs also. Listen carefully. Whenever there is any molecule, we know how to find the hybridization means by using the formula half into V plus M minus C plus A. Clear? Now let us see what is the hybridization in this thing. Means half into inert gases, lone pair unpaired electrons will be, or valence electrons will be 8. Fluorine atoms are 6. So it will be 7. So sp3 d3. D3 hybridization. How many bond pairs are there? Means see, bond pairs are nothing but atoms surrounding the central atom, 6. Lone pairs is equals to 7 minus 6, that is 1 will come. So any compound you take, you can find number of hybrid orbitals by using the formula half into V plus M minus C plus A. How to find the bond pairs means number of atoms surrounding the central atom is nothing but the bond pairs, and lone pairs is equals to number of hybrid orbitals minus atoms surrounding the central atom. This lone pair concept is useful in the Vesper theorem. I will make a separate video on the Vesper theory. In this case, we will just see how to identify the lone pairs and then bond pairs in a complex, because based on this only number of questions they will be asking you. Come to XeF4, half into 8 plus 4 by 2. So it is 6, means it is sp3d hybridization. sp3d or sp3d2. 6 are there means sp3d2. Bond pairs is equals to 4. Lone pairs is equals to 6 minus 4, that is equals to 2 will be coming. So be careful with this. Lone pairs is equals to hybrid orbitals minus bond pairs. XeF2 means half into 8 plus 2 by 2, 5. So it will be sp3d hybridization. Bond pairs are 2, lone pairs is equals to 5 minus 2, that is equals to 3 will come. XeO4, half into 8. So it is 4, sp3 hybridization. Bond pairs is equals to 4, lone pair equals to 0. XeOF4, half into plus 4 by 2, so 6 will come. So it is sp3d2 hybridization. Bond pairs, how many atoms are surrounding central atom means 4 plus 1, 5 are there. Lone pairs is equals to 6 minus 5, that is equals to 1 will come. ICl3, half into 7 plus 3 by 2, 5 will come. So it is sp3d. Bond pairs is equals to 3, lone pairs is equals to 5 minus 3, it is 2, H2O. Half into 6 plus 2 by 2, 4. sp3 hybridization, bond pairs. Since 2 hydrogens are surrounding 2, lone pairs is equals to 4 minus 2. Ammonia, half into 5 plus 3 by 2, 4. It is sp3 hybridization. Bond pairs are 3. Lone pairs is equals to 4 minus 3, that is equals to 1. IVR 5. Half into 7 plus 5 by 2. So 6 will come. So it is sp3d2 hybridization. Bond pairs is equals to 5. Lone pairs is equals to 1. So half into 7 plus 7 by 2. So 7 means sp3d3 will come. Bond pairs is equals to 7, lone pairs is equals to 0 will come. Like this, we can understand the any compound hybridization and number of bond pairs and then lone pairs by using this hybridization formula. You can easily understand and easily you can do. Once you get habituated to apply this formula to the different compounds, means it will become very easy for you to do the problem. So be careful with this thing. So that is about the what is hybridization, how many types of models of problems they can ask you based on the hybridization. So directly they will not ask hybridization, they will give a particular compound and based on that they will be asking you the problem. So that is the thing regarding the hybridization 2. In this hybridization part 2, we discussed about the which kind of d orbitals involved in the hybridization, how many types of bond angles are present in a particular molecule. For complex compounds, how to identify the hybridization. Do always inner or strong field ligands will guarantee you the inner orbital complexes, and for different compounds, how to find the number of bond pairs and number of lone pairs in a molecule. Number of lone pairs is equals to number of hybrid orbitals minus atoms surrounding the central atom. So that is for today's class. Clear? If you like this video, means click the like button. If you want to share with your friends, means share the video. If you want to get more notifications from my channel, means click the subscribe button and click the bell icon. And this is your Prabhakar and signing off. Bye bye.